Hey guys, Mr. Marone here. Welcome back. So we are in our final lecture, our final video of the proof unit here, where we're going to wrap up our discussion on G.SRT.B.5, where we are looking at right triangle relationships, and more specifically in this case, the 30-60-90 right triangle. So what we know about the 30-60-90 right triangle, what you can see from this diagram here on the right, is that our perpendicular bisector of a side it divides an equilateral triangle like you have here into two isosceles triangles. Sorry about the misspelling there. And what happens is this creates the hypotenuse of your new triangles is 2 times bigger than the shortest side. So just a little notation here. We've got 3 things coming out of this type of triangle. So if I were to draw ourselves a 30-60-90 right triangle, I've got a 60 and a 30. We have our hypotenuse here, and then we have 2 legs. One is distinctly shorter than the other, which is different from the 45-45-90 that we saw before. So we refer to this as our short leg, and we refer to this as our long leg. So we have short leg, long leg, and hypotenuse when it comes to a 30-60-90 right triangle. And I want to take a look at what happens when we look at these right triangles using Pythagorean theorem, just like we did with the 45-45-90, and see what we notice. So with these first 3, let's just try Pythagorean theorem and see what happens. So I've got 4 squared plus x squared equals 8 squared, and I've got 16 plus x squared equals 64, and when I subtract 16, I have x squared equals 48, and when I take the square root of 48, this can be broken into square root 16 and square root 3, and that becomes a 4. So I end up with x equals 4 square root 3 here. In our second one, 3 squared plus x squared equals 6 squared. I've got 9 plus x squared equals 36. So I have x squared equals 27. Take the square root of both. This can break into square root of 9, square root of 3. So I have x equals 3 square root 3 in my second one. In my third one, 1 squared plus x squared equals 2 squared. So I get 1 plus x squared equals 4. So x squared equals 3. So x equals the square root of 3. And as you can tell, we said that the hypotenuse was double the short leg. Okay, in all 3 of those, that's true. What we now notice in all of these, the short leg in the first one was 4, the long leg was 4 square root 3. Short leg in the second one was 3, long leg was 3 square root 3. And then in the last one, short leg was 1, and our long leg was 1 square root 3. So that tells us that we have 2 relationships that exist in this. The first one is that our hypotenuse equals 2 times our short leg. And our second one is that our long leg is equal to square root of 3 times our short leg. So when we solve for these special right triangles, what it does to shortcut it for us and avoid having to do Pythagorean theorem every time is it allows us to use these 2 relationships here, noticing that each one of them relates back to the short leg. So in all of these problems, the ultimate goal is going to be to get back to that short leg, to use that short leg in any way that we possibly can. Let's take a look at a couple examples here. We've got about 6 examples we're going to look at. I am going to do the first one with you, then I'm going to pause the video and let you guys try the next 5, and then I'm going to discuss a couple of them as we go through it. So the first one, they gave us, I tend to label my triangles. So across from my 30-degree angle is my short leg. I use SL. Across from my 60-degree angle is my long leg. And then I have my hypotenuse. LL for long leg, HYP for hypotenuse. And we said our 2 relationships were that our hypotenuse equaled 2 times your short leg. And we said that our long leg was square root 3 times the short leg. In this case, they gave us the short leg as 7, so my long leg equals square root of 3 times 7, and my hypotenuse equals 2 times 7. So in this case, x would equal 14, well, that's right there, 14 centimeters, and my long leg, y, equals 7 times the square root of 3 centimeters. We can just leave it in terms of radical. Okay? So there's number 1. Try 2, 3, 4, 5, and 6, and you think you're going to notice some stuff, especially when you get to 4, 5, and 6. So I'm going to allow you to do 2 and 3, actually. We're going to make a change in mid-video. Try 2 and 3. I'm going to come back, and then I'll walk through 4 and let you try 5 and 6. All right, welcome back. Hopefully you were able to get 5 and 5 square root 3 for x and y in the second one, and 8 and 16 for x and y in our third one. In our first one, they gave us the hypotenuse, so I divided by 2 to get my short leg, then multiplied by square root of 3 to get my long leg, and then I divided by square root of 3 with the long leg given to get x, my short leg, in the third one, and then I doubled that to get y, my hypotenuse. Now what we really run into is when we get a problem like number 4 here, where they gave us the long leg, but there's no radical for us to divide out. So in order to solve this, we set our long leg equals square root 3 times the short leg. So I'd have 9 equals square root 3 times x. I'm going to divide both sides by square root of 3, but the issue I run into is that we can't divide a number by a radical. So we have to do what's called rationalizing. I'm going to multiply. This is kind of what I refer to as math black magic. I'm going to multiply top and bottom by radical 3 here on the left-hand side. What I'm really doing is just multiplying by the number 1. Any number divided by itself is 1. And what this does is it cancels out the radical on the bottom. I end up with radical 9 underneath, which is just 3. And then on the top, I end up with 9 square root 3 over 3. 9 divided by 3 is going to give me a 3 on the top, and I'm left with 3 square root 3 for this left-hand side for x. All by doing what's called rationalizing my denominator, getting rid of that radical in my denominator. And then in order to get y, I just double this. And when I multiply this by 2, I end up with y equals 6 square root 3. We can't multiply the 2 by the radical, but we can multiply by what it is, the whole number that it's attached to. So 3 times 2 is 6. So I'm going to pause the video here and let you guys try 5 and 6, and then we'll discuss and we'll come back to this, and I'll show you the answers as you come back. Okay, welcome back. So number 5 was very similar to number 4. We're going to divide both sides by square root of 3 to get x on its own. And it does require me to rationalize the denominator, and I end up with 21 square root of 3 over 3, and that simplifies to 7 square root 3 for x. And I would just double the number outside the radical to get y, and I'd end up with 14 square root 3. What's nice about number 6 is that when we divide both sides by radical 3, having that radical 6 on the top allows us to do a little bit of arithmetic here. Radical 6 divided by radical 3 is leaving us with a radical 2 on the top. And it allows us to not have to rationalize. We end up with 5 radical 2 for x, and then we double that to 10 radical 2 for y. So you guys have your final homework assignment for this packet, leading up to our big test to wrap up the proof unit. So good luck on those problems. Bring in any questions you have into class, and we will look at them then.